In this video, we're going to talk about the combined gas law, where we combined all those gas laws we've learned already. Here's what it looks like. We have pressure times volume divided by temperature. So let's go ahead and assign those values. P1 is my initial pressure in atmospheres torr or millimeters of mercury. Volume, V1 is my initial volume in milliliters or liters. T1 is my initial temperature. It's given in degrees Celsius, but we now know we got to convert that to Kelvin. My final pressure is going to have units matching P1. My final volume, units matching V1, and my final temperature, again, eventually I want it back to degrees Celsius. I know that to convert from degrees Celsius to Kelvin, I add that 273 conversion value. Let's take a look at an example. Here I have the pressure on a confined gas started out at 285 millimeters of mercury, and the volume is 450 milliliters, at which point the temperature of the gas was 22 degrees Celsius. If the pressure were to be changed to 315 millimeters of mercury, the volume changed to 370 milliliters, what would the Celsius temperature be then? So we have pressure, volume, and temperature. Means we need the combined gas law, all three variables. So I pull out my given. Here's my initial pressure, my initial volume, and my initial temperature. And here's my final pressure, my final volume, and the final temperature that I'm solving for. Before I can do anything, I have to convert that initial temperature to degrees Kelvin. I add that 273. I substitute in all my givens, and here's what I get from my combined gas law. I see here that I'm trying to solve for T2. Well, the easiest way to do that is to take the reciprocal of both sides, and then T2 moves to the numerator, not breaking any laws of math. Now I need to multiply by 315 and 370. So this is what I get. I plug all that into my calculator, and I get 262.64. Remember, that's degrees Kelvin. So I have to remember to subtract off that 273 to convert back to Celsius. I do that, and I get a temperature, final temperature of negative 10.36 degrees Celsius. Let's take a look at another example. In this example, a weather balloon is filled with 15 liters of helium at a temperature of 25 degrees Celsius and a pressure of 685 millimeters of mercury. What is the pressure in millimeters of mercury of the helium in the balloon in the upper atmosphere when the final temperature is negative 35 degrees Celsius? And the final volume becomes 34 liters if the amount of the helium does not change. Okay, so now we know that we're using pressure, volume, and temperature, so it means the combined gas law. I pull out my givens. I have an initial pressure of 685 millimeters of mercury, an initial volume of 15 liters, an initial temperature of 25 degrees Celsius. I don't know my final pressure. That's what I'm looking for. My final volume is 34 liters, and my final temperature is a negative 35 degrees Celsius. First thing I have to do before I can use those gas laws is to convert all my temperatures to degrees Kelvin. So I do that by adding that 273, and now I have my initial temperature was 298 degrees Kelvin, and my final temperature was 238 degrees Kelvin. I substitute in those values. I'm trying to solve for P2, so I need to get rid of the 238 and the 34. So first I'm going to multiply both sides by 238. Then I'm going to divide both sides by 34. And I end up with a final pressure of 241.35 millimeters of mercury, which you could round off to 241.36 millimeters of mercury. This completes the combined gas law video. If you have any questions, please don't hesitate to ask.